So in last lecture we have started with the unit gravitation from mechanics 2, and in last lecture we have seen that Newton for the first time gave the force between any two objects having masses m1 and m2 that is directly proportional to the product of their masses, and it is inversely proportional to the square of the distance between them. So this type of force is called as a gravitational force field, which is a central force field, and being as a central, so central force means it is only a function of the distance, and the central force is also irrotational. Now suppose if this is a sun and this is a earth, let r be the distance between the earth and the sun, and this let this earth moves here. So let this be the position of the earth right now. Now this distance will be also r. Let this distance be theta, and now suppose after time dt, so the distance covered by this earth in time dt, let it be d theta. So d theta be the angular displacement in time dt. Now we know that this earth is revolving in the elliptical orbit around the sun. So this distance is given by r into d theta. So this r into this d theta. So this distance is given by this r d theta. Let s be the sun. So this is the earth, and let this be O. So in triangle SEO, so the area of this triangle can be given by 1/2 base into height. Now we know that this is the base of this, and this is the height of this triangle. So r is the base, and this height is r into d theta, so which is equal to 1/2 r square d theta. When you are considering an elliptical orbit with a very large radius, then this small displacement d theta could be supposed as a straight line. Therefore, even if this is a curve, as compared to this r d theta is very small, therefore we can take it as a straight line. We have taken this geometry as a triangular geometry, and the area of this geometry is just given by 1/2 base into height, so it will be 1/2 r square d theta. So let's call it as a dA. Now let me divide it by dt, so it will be r square d theta upon dt. Now this term, it is called as a aerial velocity. So aerial velocity is dA upon dt, and now we have calculated it as a 1/2 r square d theta upon dt. We know that L is equal to r into p. This is a relation between the linear momentum and angular momentum. This p is a linear momentum. P is equal to mv. So let us put the value of this p as mv, r into m into v. So v is nothing but r omega. We know that this v is equal to r omega. So this is the relation between the linear velocity and the angular velocity. So we can get m r square omega, and this omega is nothing but d theta upon dt. So the angular displacement per unit time is nothing but the angular velocity omega. So let us just put the value of this omega, so which is the d theta upon dt. So d theta upon dt can be written as L upon mr square. So let us just put the value of this d theta upon dt into this equation. Let me call it as equation number 1. Therefore equation for a dA upon dt will become 1 half r square into L upon mr square. So this r square will get cancelled and L upon 2m will be the dA upon dt, which is nothing but the aerial velocity. Now if this is the aerial velocity, so distance covered in one time interval t or in a one revolution could be given as, so this S is equal to, so this is aerial velocity into the time period t, or the velocity is equal to displacement upon time, or the displacement is equal to velocity into time. So velocity is nothing but aerial velocity, which we have calculated as L upon 2m, and t is the time period. So this is the distance covered in a one revolution with the aerial velocity dA upon dt.